Okay, now we're on to 5-3, which is graphing square root and cube root functions. You're going to notice once we get into the more complicated graphs that they follow the same pattern as the other functions we've looked at with the horizontal shift, vertical shift, stretch, and reflection. So just kind of keep that in mind. Okay, so if we are looking at this is our square root function, which is f of x equals the square root of x. We can also look at that now that we're good at rational exponents as f of x to the 1/2 equals x to the 1/2. So I'm just going to plot some points. I'm going to take the square root of 0, square root of 1, square root of 4. You notice I'm using perfect squares. That's the reason I'm doing that. Every number has a square root, but of course these are the easiest ones to deal with. So I'm going to have 0, 0, 1, 1, and 4, 2. Be my point here. So this is the parent function for a square root function. Okay. All right, and the domain is, since we can't plot the square root of a negative number because that's an imaginary number. So their domain is x has to be greater than or equal to 0, and at the same time we're only dealing with our positive roots. Okay, so we will have our range is all y values that are equal to or greater than 0 as well. Okay, what happens when we multiply that radical by a value of a? So just like in our other functions, we know that's going to stretch that function out by a value of a. So let's take that same parent function now and just multiply it by 3. So we have the square root of 0 times 3. Square root of 0 is 0, times 3 is still 0. 3 times the square root of 1. Square root of 1 is 1, times 3 is 3. 3 times the square root of 4. Square root of 4 is 2, times 3 is 6. So I've got my parent function kind of graphed here so we can see how it changes. And now my new points for that would be 0, 0, 1, 3, and 4, 6, way up here. So I took that same curve and just stretched it out. If my stretch, or my compression in this case, is just 1/2, it's going to take each of those values and divide it by 2. So I can actually write this as square root of x divided by 2 as well. Those are the same thing. So square root of 0 divided by 2 would just be 0. Square root of 1 divided by 2 is 1 divided by 2, which is 1/2. And square root of 4 divided by 2 is 2 divided by 2 is 1. So if I graph those, let me do that in a different color. I would have 0, 0, 1, 1/2, and 4, 1. So it's the same curve, just stretched out horizontally. Okay. Let's go down to our shifts if we're going to shift from within the radical. And remember, just like we have with our other functions, that h value that's within parentheses, or in this case within the radical, is going to adjust our horizontal shift by the opposite, because it's whatever takes you back to just x. So I'm going to graph it on this same line. So if I had, let's say we had f of x equals the square root of x plus 2. I know that that would shift, actually let's make this minus 2. That would shift that to the right 2, but the rest of my curve would stay the same. So here for my next point I went up 1 over 1. I would go up 1 over 1. My next point I went up 2 over 4, so I could go up 2 over 1, 2, 3, 4. So it has exactly the same curve as the parent function, it's just shifted to the right 2. If I were to shift this, that k value always controls our vertical shift. So let's say I had f of x equals the square root of x plus 3. That's going to shift my entire function up 3. So, well, let's go back to here a minute. So my new vertex here is going to be 2, 0, my new essential point. Here, my new essential point is going to be 0, 3. It's just shifting it up 3. So I'm going to go up 1, 2, 3, and just like I did with my parent function, I can go up 1 over 1, up 2 over 4. And so now that goes along with this f of x equals the square root of x plus 3. Okay? Let's go down to example 1 and 2. We'll just put all of those together. So the most important thing to do first is find your essential point, or essentially your vertex. So because this is a shift of the opposite horizontally, that controls my x value. The 4 is my vertical shift, which controls my y value. So my new starting point for this function is actually at 3, 4. So I'm going to go over 1, 2, 3, and go up 1, 2, 3, 4. So let's think about what we have in this one. We have a horizontal shift to the right, 3. We have a vertical shift up 4, and we have a stretch of 3, which means from the parent function, normally I go up 1 over 1. Now I need to go up over 1 up 3. So 1, 2, 3, because it's stretching that out. The next one I normally go up 2 over 4, but in this case I need to go up. Now I would have to go up 6 and over 4. So, and if this, that kind of gets confusing, so let's put those values in. So if I know 3, 4 is my beginning, let's go ahead and just plug in my next point, which would be 4. So I have 3 times the square root of 4 minus 3 plus 4. So 4 minus 3 is 1. Square root of 1 is 1 times 3 is 3 plus 4. So my next point would be at 4, 7. So here I have 1, 2, 3, 4, up 1, 2, 3, 4, 5, 6, 7. That'll be my next point. If I go over 1 more than that, I go up to, if I actually put in my next x value as 5, that's not going to help me, because if I put in 5 minus 3 is 2, I want to look for the next one that's going to give me a perfect square. So if I need this answer in here to be a 4, my next input is actually going to be a 7. So I'm going to plug in for 7 and get 3 square root of 7 minus 3, which will give me 4. That's a perfect square, plus 4. So I get 3 square root of 4 is 2, plus 4, so my next point would be a 10, and that's at 7, 10. So I go over 1, 2, 3, 4, 5, 6, 7, up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So same curve. Now, the other thing I want you to be aware of is it's not going to drop below that line. Essentially, once you find that new beginning point, that y value becomes your new asymptote. And that function is not going to drop below that line. So this is your horizontal asymptote. Okay. So let's go to example 2. Let's think about what we have going on first. So we have, because of that, we've got a reflection, which means it's going to flip our function over. My new starting point is going to be the opposite of this and this. It's going to be -2, -3. The rest of it should be fairly straightforward. So all I have to do is, instead of my curve looking like a parent function, it's going to be the mirror reflection of that. So my new point is at -2, -3. Normally I would go up 1 over 1 to the next point, but I'm going to go down 1 over 1 to the next point. And then I would normally go up 2 over 4. In this case I'm going to go down 2 over 1, 2, 3, 4. And now my asymptote is at -3, and my curve is going to look something like that. Okay, so now with cube-root functions, we actually can go below the x-axis. The difference is it's going to shift and change directions this way. And the reason it does that is because we can now incorporate cube roots of negative numbers. So cube root of -1 is -1, cube root of 0 is 0, cube root of 1 is 1. So this is actually the parent function for cube roots. And it kind of has this little S-shaped curve to it. So the domain now is all real numbers. Now there's no number that we can't find a cube root for. Positive, negative, 0, they all work. And the range is unlimited. We can have any answer there. So, like we were talking before, your A value controls your stretch or compression. Your H value, and sometimes you'll see when A is greater than 1, they will consider that a vertical stretch. You may see this sometimes, vertical stretch. And then when A is less than 1, it'll be a horizontal stretch. Sometimes you'll see that differentiated. Your H is your horizontal shift. And your K is your vertical. Remember that your horizontal shift is by the opposite value. Okay? Alright, so again, you're going to have new starting points with these. So if, in this case, our new starting point would be 4, negative 2. Sorry, 4, negative 2. So my new starting point is going to be 1, 2, 3, 4. It's going to go down 2. Now, since I know on my parent function, I can go from 1 point over, I would just do that. I would use my points as 5 and 3 in order to graph this one. So 5 minus 4 is 1. The cube root of 1 is 1. Times 2 is 2. 2 minus 2 is 0. So my next point would be at 5, 0. And then if I do 3 minus 4, I would get negative 1. Cube root of negative 1 is negative 1. Times 2 is negative 2. Minus 2 is negative 4. So we go at 3, 3, negative 1, 2, 3, 4. So this is still going to have that kind of S curve. It's just stretched out because of that value of 2. Okay. Alright, example 4. I have a new starting point of negative 4, 3. And again, I'm just going to go 1 point above and below, because to me that makes sense. If I use negative 5, I'll get negative 1 within the radical. If I use negative 3, I'll get 1 within the radical. So I'm going to use negative 3 and negative 5. And so for negative 3, I get the cube root of negative 1, which is negative 1. Sorry, 4 minus 3 is 1. Cube root of that is 1 times 3/4 would be 3/4 plus 3. So I get 3 and 3/4. And then negative 5 plus 1, here's your negative 1. Negative 1, the cube root of negative 1 is negative 1. Times 3/4 is negative 3/4 plus 3, which would be 2 and 1/4. So I've got negative 4, 1, 2, 3, 4, and up 3, 1, 2, 3, and then negative 3, 3 and 3/4, and so this one is stretched out just by a little bit. Okay. All right. Just remember that sometimes you will see these written in fractional exponent form, but the same rules still apply. I want you to try 5 and then example 1 and 2 on the bottom and come back and check against mine. Alright, so I apologize for kind of my little squiggly lines over here, but here's your example 5 and 1 and 2. I want you to notice that the cubic functions don't have an asymptote, and that goes back to the fact that their domain and range is all real numbers, so they have no or they're limited, but the square root functions always will have an asymptote that they can't go below. That's it. Thanks.